Today's lecture is the Starry Messenger, Galileo and this telescope. In this lecture, we're going to meet one of the greatest astronomers of the Renaissance period, Galileo Galilei, and look at his marvelous discoveries with the newly invented telescope. Galileo Galilei was born in 1564. He was an Italian contemporary of Johannes Kepler. Like Kepler, he grew up in the generation after Nicholas Copernicus and was deeply steeped in the arguments about the Copernican system. He was a gifted mathematician and experimentalist who strongly preferred experimentation and measurement to philosophical rhetoric as a style of argumentation. This was a time of great intellectual fervent in Italy and throughout Europe in general. But the general academic style of the time was to argue from first philosophical principles. If one's arguments were beauty, it didn't seem to matter whether they corresponded to measurable reality or not. Galileo had no patience with this particular style at all. This may in part be because of his upbringing. He was born into a musical family. His father, Vincenzo, is a famous composer, especially of lute works, and did extensive work on music theory. Galileo was steeped in mathematical descriptions of natural phenomena. The idea that music and mathematics are deeply entwined goes all the way back to Pythagoras. As a consequence, Galileo preferred to show that things were true by experimentation and observation, not by airy flights of logic. As a consequence, he became very quickly a staunch or anti-Aristotelian and found himself often at odds with the intellectual establishment of the time. Galileo gave as good as he got. He loved a good argument and did not suffer fools gladly. This had an unfortunate consequence of making Galileo a number of enemies, especially among the intellectual elite of the time that was to come back and haunt him in later life. In a letter to Kepler in the year 1597, he wrote, "Like you, I accepted the Copernican position several years ago, and discovered from thence the cause of many natural effects which are doubtless inexplicable by the current theories. I have not dared until now to bring my reasons and refutations into the open." While Galileo was showing his hand in a private letter to Kepler, this letter expresses the intellectual climate of the time. The Copernican idea had been around for nearly half a century, but it was not widely accepted and was beginning to be viewed with suspicion not only by the intellectual elites of the university, but by the Roman Catholic Church itself. At the time, the arguments between the Ptolemaic and Copernican system came down to philosophical arguments, to the available observations that were made with the naked eye. Tycho Brahe, who we saw in the previous lecture, had pushed the ability of people to make naked eye observations to the absolute physical limits of the human eye, measurement accuracies of 1 to 2 minutes of arc. At this point, very little further progress was going to be made until a way could be found to overcome the limitations of the human eye. Further progress was going to require a change in technology, and that technology was soon to arrive. It became, as a start, in perhaps the most unlikely place. Hans Lippershey, all we know about him is he died in the year 1619, was a spectacle maker living in Holland in the city of Middelburg. In October of the year 1608, he sent to the Dutch States General an application for a patent on a device that, quote, "by means of which all things at a very great distance can be seen as if they were nearby." This patent application was denied, and the reason that the examiners from the States General gave for their denial was that the principles of the device that Lippershey was describing were simple and broadly known, and that there were many other examples of the device that had appeared in the same year. Indeed, news of this invention began to spread quickly through Europe. What Hans Lippershey was describing were the first primitive telescopes. The first word that Galileo had of these telescopes likely came through the background buzz of gossip in the time. One of the entertainments of the late 16th and early 17th century were traveling shows of wonders, little portable museums of the latest curiosities of the world. This included people bringing around these farseers, to give the German translation of the word, devices that when looked through could allow a church steeple to appear 3-4 times closer than it actually was. They were great curiosities, and word about them spread quickly through Europe. In August of 1609, Giambattista della Porta, a friend of Galileo's, sent a letter to him describing in there his experience of one of these telescopes which had come with a traveling show through his part of Italy. Galileo had been unsuccessful in catching up with one of these shows, and so himself had not seen a telescope, but Della Porta, having seen one, Galileo importuned him to describe the device further. The sketch you see at the top of the page should look very familiar to anyone who's seen a modern spyglass-type telescope. It consists of a long tube with a lens at one end and a smaller tube that inserts into the other end that carries a second lens. The eye is put to the smaller second lens and used to form an image from the light gathered from the larger lens at the other end of the tube. The smaller tube can slide in and out of the larger tube to allow the user to bring the image into a sharp focus. We immediately recognize this as a telescope, and indeed, this is the first recorded drawing of a telescope. When Galileo received this, using no other information except his knowledge of optics, he realized he had to have one. Galileo used his knowledge of optics to make an improved design based on the Della Porta sketch. He learned how to make his own lenses, he imported the best glass from Murano, Italy, he built lens grinding equipment, and he solved quite a number of difficult technical problems in the production of the curved lenses. He also came up with a new and innovative design of telescope that was much more useful than the simple telescope spyglasses that were running around Europe at the time. He steadily improved the optical quality of the telescope, building better lenses and coming up with new ways to get around the limitations of the glass lenses that he was able to make, and eventually achieved increasing magnification, eventually developing a telescope with approximately 20 times magnification. For our purposes, what a 20 times magnification does for a telescope is it makes the object look 20 times larger than it would appear to the naked eye. That's equivalent to making it look as if it is 20 times closer. This is very modest by the designs of modern telescopes. You can go out and buy at a department store a telescope capable of magnifications over 100. A typical pair of binoculars easily achieves 20 or 50 times magnification, are commercially available and readily today. But at this time, in late 1609, 20 times magnification was state of the art, and it was enough to allow Galileo to make marvelous discoveries when in the November of the year he turned it on the sky for the first time. These are pictures of Galileo's surviving telescopes. They live in the Museum of Science in Florence, Italy. They consisted of long tubes covered in leather to make them pretty. Basically, they were cardboard or light wooden tubes. The main lens was up in the top. A small the big objective lens was up in the top. The smaller eyepiece lens was at the back and could be focused by means of a small sleeve that allowed this lens to be moved in and out of the larger tube to bring it into focus. We recognize this design right away. In this fancy mounting built in the 19th century, we can see the remnants of one of the original objective lenses, long since shattered over the many years in which this telescope has existed. The Galilean design of telescope starts with a very conventional objective lens, a double convex lens looking like a lentil bean seen in profile. Indeed, the word lens and lentil are related. This larger lens gathers light and brings it down to a focus. But before that light comes to a focus, Galileo interposed a double negative lens, a double concave lens. By introducing a double concave lens, he bends the rays out to where they can then enter the human eye at the right hand of this diagram. By using a negative lens instead of another smaller positive or positively curved lens as the eyepiece, the image formed by Galileo's telescope comes out right side up, not inverted as in the common two-lens spyglass design. This was of tremendous utility. In fact, so useful it was that Galileo first applied the telescope to trying to sell it to the estates, to the local governments, including the Doge of Venice, bringing it to them for both its potential maritime applications, since Venice was the great seagoing power of the time, as well as for its potential military applications. But it is Galileo's astronomical applications that give us the greatest interest. Galileo made a series of observations in 1609 that stunned him. The universe that he saw through his telescope was different than the one you saw with the naked eye. It was clearer, and he discovered many new wonders. Had he just stopped there or written a few letters, we probably would have not given it much importance. But Galileo was one of the best writers of his day, and he wrote a pamphlet in the year 1610 entitled The Sidereus Nuncius, the Starry Messenger, in which he described his observations made with the new telescope, illustrated with his own hand sketches and engravings, showing in detail what he had seen to the world. The Starry Messenger was short, sweet, and to the point, and it created an immediate sensation in Europe and made Galileo immediately famous throughout the continent. Later observations were to be published in the year 1623 in a book entitled The Assayer. Between these two books and numerous letters that were to flow between Galileo and his numerous colleagues between 1610 and 1623, Galileo's observations with the telescope were to open up a completely new universe to view. What could before was not even thought of could now be seen clearly by anybody with a telescope. Now, there are many of these observations, but the most important to us here are as follows. He described craters and mountains on the moon. He found spots on the sun and used them to measure the rate of solar rotation. He discovered the 4 bright moons of Jupiter, and he discovered that Venus goes through a pattern of phases. Let's look at each of these discoveries one by one. The first discovery is that the moon has craters and mountains. Many of us who ever look at anything in the sky with a telescope, the very first target you turn it upon is the moon. It's easy to find, it's big and bright. And in Galileo's telescope, the moon, which, while it looks multicolored, dark and light patches, but otherwise very smooth to the naked eye, suddenly snaps into enormous detail and sharp relief when viewed even through a modest telescope of 20 times magnification. The surface of the moon is seen not to be smooth, but to be covered with vast numbers of craters, high mountains casting shadows in the sunlight, and those dark spots are seen to be vast plains very lightly cratered. The moon in the telescope appears not as simply a smooth, mottled ball of light in the sky, but appears as another world, a world with terrain and features and geography just like the Earth. It made the moon something very different in the consciousness of Europeans. The second observation, which was done after the publication of the Sidereus Nuncius and described in a series of letters called now the Sunspot Letters, was to do a series of observations of the sun. It was noticed or believed that the sun was a bright, featureless disk. It was, after all, one of the essences of celestial purity in the Aristotelian view of the world. But viewed through the telescope, or more precisely viewed with the telescope with a projection system, because you'd damage your eyes if you attempted to view the sun directly, even with a modest telescope like Galileo's, it can be seen that the sun's surface is not perfect and smooth, but in fact is mottled and occasionally has a number of dark spots that come and go and change in time. The sun, unlike the Aristotelian idea of unchanging celestial perfection, is indeed a place of continuous change. These patterns of spots, however, don't just sit there. They can be clearly tracked as they move across the face of the sun. By watching this pattern day after day through a group of sunspots on the sun, Galileo was able to discover that the sun is rotating about its axis, and that this rotation takes approximately 25 days to complete. This was a stunning observation. In addition to the whole philosophical idea of the sun not being a perfect body, the fact that it rotated was absolutely anti-Aristotelian. The argument had been made by Aristotle and others that the Earth could not rotate because it was too big to. The larger the mass, the more the stuff of an object was made of, the more it would seek a state of rest. But here was an object, the sun, bigger than the Earth, and it was in rotation. If the sun could be in rotation, why could not the smaller Earth also be in rotation? Remember, Galileo, Kepler, Copernicus all knew of the work of Aristarchus and his attempts to estimate the sizes and distances of the moon and the sun. Taking the Aristarchan data at face value, whatever their flaws, the Sun was much bigger than the Earth. To see it in rotation was to then ask the question, should not the Earth also be able to rotate? This was one of the many blows these telescopic observations were to land against the Aristotelian view of the world. One of the most amazing discoveries of Galileo, and the one that made his immediate fame in 1610, was his observation that Jupiter is not alone in space. The planet Jupiter, when looked at through the telescope, is seen as a banded disk. We now know these to be the immense cloud bands of a gas giant planet. But more than that, Galileo discovered that Jupiter is accompanied by 4 bright moons, what we now call the Galilean satellites of Jupiter, and have given the Greek names Io, Ganymede, Europa, and Callisto. As he watched Jupiter hour after hour, night after night, with his telescope from Pisa, Italy, he began to see that those 4 moons were clearly circling around Jupiter. As Jupiter moved across the sky against the background of stars, the moons followed. Their center of motion was on Jupiter. The Aristotelian view of the world that the center of all motion in the universe was the Earth, lying at the center of a geocentric system. But here was putting the lie to that. Jupiter, one of the planets, a bright one to be sure, has 4 moons, and they circle it, a solar system in miniature circling around the planet Jupiter. This showed incontrovertibly that there are other centers of motion in the universe besides the Earth, and that if an object in motion, Jupiter, could have a group of other objects in motion around it, keeping up, then that really took a huge bite out of the Aristotelian view of the world. It simply could not be explained in the context of Aristotelian physics, and it was totally unexpected before the invention of the telescope. You could not see these moons with the unaided eye. Finally, the greatest blow landed on the Aristotelian and Copernican and Ptolemaic view of the universe was that Venus showed a full sequence of phases just like the moon. The photograph that I show here was taken in 2002 through approximately 1/2 of a Venus orbit and shows Venus going from a very large crescent to a progressively smaller half Venus to finally an even smaller gibbous Venus. These angular sizes are in their proper proportions. Venus will appear to have a relatively large angular size when close, a relatively small angular size when far away. And yet the pattern of phases tells us the direction of the sun and the illumination of Venus, which shines by reflected sunlight, giving us a very important information about the configuration of the Earth, Sun, and Venus. This is the sketch shown down here in the corner from the Il Saggiatore of 1623, showing this very same pattern of the phases of Venus that are visible in the photograph. I'll point out in passing that there are 3 other planets shown in this picture. Mars and Jupiter also show disks when viewed from the telescope, and Saturn shows not only a disk, but a pair of odd-looking handles. Unfortunately, Galileo's telescope was just not quite good enough to be able to show that those handles were really the rings, that the handles of Saturn were really what we now know are the rings of Saturn, would be discovered by a Dutch astronomer, Christian Huygens, using a larger and better telescope in later decades. But getting back to Venus, what this pattern of phases shows incontrovertibly is that Venus orbits the Sun. Let's see how this works. On the left, I've shown a sketch of the Copernican system. In the Copernican system, Venus is the second planet from the Sun, and Earth is the third. Venus orbits on a smaller orbit, which is sometimes closer to the Earth than the Sun, and sometimes further than the Sun from the Earth. As we go from positions 1 to 2, 3, 4, 5, and 6 around one pattern of orbits by Venus, when Venus is at position 1, I can only see a thin sliver. I expect Venus to be a crescent, but Venus is very close, so I expect it to have a large angular size in the sky. When Venus goes to position 2, I can see half of the illuminated face from the Earth, and Venus is further away, so a little bit smaller. By the time it's reached position 3, I can see a gibbous or nearly full face, but it's further away, and so its angular size is smaller. I can't see Venus in the glare of the sun when it's immediately behind the sun, so it's really hard to see a full Venus, but as Venus comes out from behind the sun in the Copernican view, it should be a small gibbous, then a larger half Venus, then an even larger crescent Venus. And so seeing exactly that pattern of phases and sizes that were seen in Galileo's telescope. Large crescent to smaller half to smaller still gibbous, and then patterning back up again. By contrast, in the Ptolemaic system, Venus was on the circle between the Earth and Mercury, and the Sun was in the distance. The epicycle of Venus is tied to a line from the Earth to the Sun, which is why Venus always appears to within 47 degrees of the Sun in the Ptolemaic system. As Venus goes through one of its orbits, notice that it never gets further away from the Earth than the Sun is, and therefore is always between the Sun and the Earth. As a consequence, when Venus goes through its cycle of phases, when it's close, it should show a large crescent, as indeed it does at positions 1 and 6. But as it moves further away on its epicycle through positions 2 and positions 3, because it is always between the Earth and the Sun, it will always show a partial crescent phase. You will never get Venus behind the Sun in the Ptolemaic system, and so can never show a half or a gibbous phase. So the Ptolemaic system of the time would have shown a pattern of shrinking crescent phases, not the pattern of phases that is actually observed in Galileo's telescope. This was perhaps the most serious blow of all against the Aristotelian and Ptolemaic views of the world. The Ptolemaic system makes a very specific prediction as to the pattern of phases of Venus, and when those phases are visible in the telescope, they're otherwise too small to see with the naked eye. It is clear that the Ptolemaic system makes a wrong prediction. The Ptolemaic geometry is ruled out definitively by Galileo's observations with the telescope. The impact of Galileo's telescopic observations was immediate and forceful. Kepler, receiving a copy of the Sidereus Nuncius, and of course was corresponding throughout his life with Galileo, was delighted by these discoveries because they so well accorded with his belief in the truth of the Copernican description of the solar system. He begged Galileo to send him a telescope, which Galileo had so many requests he had to demur, but Kepler was not to be stopped. He quickly was able to acquire his own telescope. It didn't prove adequate to his needs, and so he began to develop new and improved designs to increase the power and optical quality. In fact, in many ways, the Keplerian design of telescope was to surpass the Galilean design for astronomical work, and at the generations after Galileo was to, in fact, variations upon the Keplerian telescope were to replace the Galilean telescope for many decades. As a consequence of Galileo's telescopic observations and his vivid descriptions in books like the Sidereus Nuncius and the Assayer, was that scholars had to begin to take the Copernican seriously as a physical description of the cosmos. Before this time, it was largely a mathematical exercise. Whether you chose the Ptolemaic way of computing the positions of the planets or the Copernican was largely a matter of choice. Both produce roughly the same preservation of appearances. They made very similar predictions to the positions of the planets. But when you added telescopic observations, the Ptolemaic system failed utterly to predict the correct phases of Venus. Similarly, you had to now begin to take seriously the idea that Venus circled the Sun, and that began to lead you to the Copernican system not as a mathematical calculation method, but as an actual physical system, a physical description of the actual cosmos. As an aside, it will be pointed out that the ability of the Copernican system to allow relatively straightforward calculations was of great utility whether you believed in it or not. The official church line was that the Ptolemaic system was the correct way of describing the actual universe, but in the Gregorian calendar reform of the generation just after Copernicus, it was the Copernican system that was used for the calculations behind the Gregorian calendar reform, calculations performed by Jesuit priests who were also astronomers. While scholars began to take seriously the Copernican system after the writings of Galileo, hardcore skeptics were not convinced. Indeed, many of those who held to this idea that pure logic and reason is the way to explore the universe, not messy observations and measurements, believed that because one had to use an artifice, a telescope, to look at the heavens, that this device was somehow distorting the view of the world and giving false information, and others went so far as to say that Galileo was just making it up. Of course, the problem with that particular argument was, if you got your hands on a telescope, anyone who looked at the sky could literally see for themselves. Seeing sometimes is believing, or at least in this case, seeing is convincing. The evidence of the eye was clear to anyone who looked through the telescope. One did not need to know Latin or follow complex and often rather difficult geometric mathematical arguments. One had only to hold up the telescope to the eye and look up at the sky and see for yourself. This began to work a tremendous change in the minds of people in the time of Galileo. Indeed, while the arguments about the primacy of the Ptolemaic versus the Copernican system were to rage for at least another century among certain groups of scholars, for the most part, no serious works seriously defending the Ptolemaic system were to be written after the 1630s. This work made Galileo immediately famous through Europe, but it also brought him into direct conflict with the intellectual and religious authorities of the day, a topic that we'll cover in the following part of this lecture.